All this work with splitting into partial fraction is leading us into using this as a technique to be able to integrate. And why this is going to be helpful is because if we look at an integral like this one here, so I've got this integral. This integral, when I try to integrate it, well, there's a problem because I can't isolate the power on x, so I can't use power rule. This is not some sort of, one I can use substitution with. If I try parts will not work on this because even though there's a times there, the parts, when I set up the parts, it won't work. So this cannot be integrated with any of the techniques we have so far. So we're stuck. But this is a partial fraction. We can split this up into a partial fraction that looks like this. And if we can split it up into that partial fraction, now we have a much easier situation because we no longer have the times in the denominator. We have the denominators split up independently into separate integrals. And we can integrate both of these using log. So 1 over x, we're going to use log. 1 over x plus 1, we can use log to integrate both of those. So when we have integrals like this, we can split them up into their partial fraction pieces, and then we can integrate these using our log function. So in this case here, we have 1 over x times x plus 1. We can split these into the partial fractions by setting up the partial fraction here. So we have a over x, b over x plus 1. We can make the coefficients equal to each other. We can set up a system of equations where we can equate the coefficients. So here I'm going to end up with a x plus 1 plus b times x, and that's going to be equal to the numerator, in this case, is equal to 1. So that numerator must be equal to 1. And we can now solve for a and b. So we end up with ax plus bx plus a is our constant, and that's going to be equal to 1. Well, we can solve this by equating some of these parts. The constant a is equal to 1. So a is equal to 1. So I can determine that. So a equals 1. And we know that the a plus b must be equal to 0 because there's no x terms on the right-hand side of that equation. So solving this then, if a is equal to 1, b is equal to negative a, so b equals negative 1. So those are two parts now. Just going to color code this one here. This one ends up being our b, which we had in red to start. So there's our b, that a value we had in blue to start. So now we have our partial fractions. We can now express this integral differently. We can express this integral as a over x, and then dx plus negative 1 over, and I'll just make sure I keep that in the same color here. So that b is negative 1, so negative 1 over its factor of x plus 1. Now we can anti-differentiate these two using logs. So this now becomes, now this is why this is an integration technique. So I went from an integral that I cannot integrate in 1 over x times x plus 1 into 1 over x plus negative 1 over x plus 1. So we end up with log x plus, well, I'm going to make that minus log x plus 1, and then don't forget the plus c. And we can combine this as using log properties, x over x plus 1 plus c, since the minus log means divide. So we will split this next example into partial fractions and integrate. So here we have 1 over x minus 2, x plus 1. So I'm going to split this into this partial fractions. So for the x minus 2, we have a denominator x minus 2, and we're going to give it a coefficient a plus our coefficient b with our denominator x plus 1. All right, so then when we work this out, this is going to end up being a times x plus 1. Let's just make sure I color code that properly. Plus b times x minus 2. And that's going to equal the numerator that we have here, 1. So that comes from that numerator 1. So working out the x coefficient, we're going to end up with ax plus a plus bx minus 2b equaling 1. So a plus bx plus a minus 2b is equal to 1. So again, grouping my terms here, that a and b here become the a and b there. The a and 2b here become the a and 2b here. And we're going to match the constants with that 1. So there's one equation. So I'm going to solve that one first. So I have a minus 2b is equal to 1. So I end up with a is equal to 1 plus 2b. And I'm going to use that in this equation with a plus b. So in the blue, I have a plus b is equal to, there's no x term, so that must be equal to 0. And then I can substitute for the a. I'm going to replace the a with a 1 plus 2b plus b is equal to 0. So we end up with 1 is equal to negative 3b, b is equal to negative 1 over 3. Okay, and if that's the case, then that makes the a value equal to positive 1/3. So now I can write my partial fractions using the a coefficient. I'm going to get an integral of 1/3 1 over x minus 2 dx. With the b coefficient, I'm going to end up with a minus minus 1/3 with the integral of 1 over x plus 1 dx. With this then, I'm going to anti-differentiate both of these. I end up with 1/3 log x minus 2 minus 1/3 log x plus 1. And then we have our plus c. And then I'm going to just combine these into one log. The positive log goes in the numerator. The 1/3 is a cube root, so I end up with cube root x minus 2. And then the denominator, we have the cube root of x plus 1, close that off, plus c.